Welcome back to week 9. This week we'll be covering chapter 35 on the special theory of relativity. Let's look briefly here before we dive into the chapter on what is relativity. And Einstein had this question that he was trying to figure out on how do you deal with, there's two different laws that he couldn't reconcile. One was that Newton's laws of motion stated that the motion of the observer doesn't matter, and then there was Maxwell, whose laws of electromagnetism showed that different laws of electricity and magnetism apply to moving charges. And he wanted laws that could apply to everything, not different laws for different things. And so he came up with a theory of relativity to deal with this problem, showing that there's a relationship between space and time, leading to his famous equation E equals mc squared. And we'll cover that equation at the end of the chapter. Now, as your book says about the ideas of relativity, these ideas are so remote from your everyday experience that understanding them requires stretching your mind. It will be enough to become acquainted with these ideas, so be patient if you don't understand them right away. We'll briefly cover here the difference between special and general relativity, because one chapter deals with special relativity, one chapter deals with general relativity. And special relativity involves only the special case where motion is uniform. It describes motion in a straight line at a constant speed, but once you accelerate or change direction or do anything to change your motion, then special relativity doesn't apply. In the cases where motion is changing, the theory of general relativity applies. So to start out the chapter, we start by looking at when you talk about motion, and the special theory of relativity deals a lot with motion, you need to know where you're measuring that motion from. And the place where motion is observed and measured is called a frame of reference. Now, an object may have different velocities relative to different frames of reference. So, for example, if you're moving alongside of an object, you may be moving at the same speed as that object, but see the object is standing still. So anyone standing on Earth next to you, you're both spinning on Earth at the same speed. So you have movement, but to each other, it looks like you're standing still, and that's based on your frame of reference. So someone on another planet watching you, they may see you both as moving at a certain speed. If someone could stand on another planet and watch you. To measure the speed of an object, we first need to choose a frame of reference and pretend that we're in that frame of reference standing still. Then we measure the speed with which the object moves relative to us, that is relative to the frame of reference. So is there some frame of reference that's actually still? And we would like to think that space itself is still, and couldn't you make measurements relative to still space? But really everything in space is moving, and everything anywhere you go is moving. So that's why making these relative measurements becomes helpful in trying to understand things, because if you tried to compare movement overall, it would be really difficult, if not impossible, to try to measure how things are moving in the larger picture of space. So there's two postulates or components to the special theory of relativity. The first one is that all laws of nature are the same in all uniformly moving frames of reference. And Einstein really liked things to be consistent. So if a law applied in one place, the same law should apply in all scenarios. And this is an example of that. And what he's saying here is that the laws of nature that apply when you're standing still are the same that apply when you're uniformly moving. So it shouldn't matter if you're moving really, really fast or you're sitting completely still, that the same laws of nature, or laws of physics, as we probably now call them, are going to apply. And the second part of the theory has to do with the speed of light. And one thing that Einstein looked at when he was younger was what would a light beam look like if you traveled along beside it. And according to classical physics, or physics in the past, the light beam would be at rest. So if you were moving just as fast as the light beam, then the light beam would look like it's sitting still next to you. So think of, you and a car moving at the same exact speed together down the road, and you would both see, you'd see the car moving at the same exact speed and be traveling alongside it. Well, what Einstein realized was that you could never move with a beam of light. So no matter how fast you might be moving, the speed of light is always going to be going by you at 300,000 kilometers per second. Now, this is a little bit hard to, it's one of those parts of the special theory of relativity that's hard to comprehend because we'd like to think that we could move alongside a beam of light at the same speed of light. But what he realized is that no matter how fast or slow you're moving, you're always going to see light going past you at the same speed. And that gives the second part of the special theory of relativity, is that the speed of light in free space has the same measured value for all observers, regardless of the motion of the source or the motion of the observer. That is, the speed of light is a constant. One interesting consequence of the second postulate or second part of that special theory of relativity is the idea of simultaneity. So we say that two events are simultaneous if they occur at the same time, and two events that are simultaneous in one frame of reference may not be simultaneous in a frame moving relative to the first frame. So they give the example in your textbook if they turn on a light in the very center of the compartment of the rocket, and the light will travel out. If they could actually see the light traveling, they would see the light travel out equally in all directions, and it would hit the front end and the back end of the rocket compartment simultaneously or at the same time. However, if someone was standing on the ground watching the rocket go by, they would see the light in the center of the compartment moving more quickly toward the back of the compartment than toward the front of the compartment. Because the ship is moving forward, the light going to the back of the compartment would have less distance to travel. So by the time the rocket moves forward, the front of the rocket has moved further away, making it the light have more distance to travel, and the back of the compartment has moved closer to that light source, giving it less distance to travel. So because of the ship's motion, the light that strikes the back of the compartment doesn't have as far to go and strikes sooner than the light that strikes the front of the compartment. And these two events do not occur simultaneously to the observer standing on the ground watching the rocket go by. And that is, again, if you could see the light and where it hit. So essentially, this simultaneity is saying that in one frame of reference, you might see an event occurring simultaneously, and in a different frame of reference, the event may not be occurring simultaneously. Common sense would tell us that we would think that regardless of motion going on, that the light would be hitting at the front and the back at the same time, but it doesn't. And so this is one of those things that's hard to try to wrap your mind around and make sense of. But hopefully what can make sense is that in both cases, the speed of light is constant. So if we take a measurement from either location, we see the speed of light is the same, but whether we see the events as occurring simultaneously to each other is relative to our position. We usually think of the space around us as three-dimensional. You've probably learned about these dimensions in math, such as the x, y, and z axis, where the x-axis might be east to west, the y-axis north to south, and the z-axis up and down. For example, if you were to build a box, you could measure the height, width, and length. These are three dimensions. You could call this height, width, and length x, y, and z. And hopefully this seems logical. Most of us have measured things and measured height, width, and length before. But the only thing that we're not taking into account with our measurement is time. And in this theory of relativity, time is very important. And the reason that it's important is that if you look in the past, before the box was built, the box was used to not be a box. And in the future, the box may not be exactly the same as it is now. Things can happen, like it can warp, be smashed, be weathered, and all of these things will change the box in the future. So our measurement is only accurate at a certain moment in time, and we call this space-time. Space and time are intimately linked together. They exist in space-time, so each person, each planet, each star, each galaxy exists in what physicists call the space-time continuum. And two observers next to each other would measure the same intervals of space and time. Two observers moving at different speeds, however, would have different measurements of space and time. And at ordinary speeds, this difference is not noticeable, but as we get closer to the speed of light, these differences become much more significant. So the difference in measurements of space and time aren't random. The measurements differ in a very specific way, such that each observer will always measure the same ratio of space and time for light. And the constant ratio of space and time for light is c. And so what this means is that if you divide, no matter what space you're looking over, divided by a certain amount of time, you're always going to get that space divided by time will always be the same value. We'll go over in just a minute what that means. But essentially, the ratio c is the unifying factor between realms of space-time. No matter what speed you're looking at or over what time frame, when you take the space divided by the time, you will always get that value c, which again, c is the speed of light at 300,000 kilometers per second. Now, the constant ratio of space and time for light is c, and let's look at why this is. What this formula in pink on the left there is saying is that if you measure something over a small amount of space, then that measurement will take a small amount of time. Equaling space divided by time will equal a value of c. If you were to measure something over a larger space and divide it, that same event would take a longer amount of time or a larger amount of time, and dividing space by time for that event would also equal c. Let's look at this case here. So in picture A below, an observer moving with a spaceship would see a light being shown from the bottom mirror to the top mirror and bouncing back and forth between the mirrors as moving, they'd see the light as moving vertically, straight up and straight down. A person standing on the ground would see the light start at the bottom mirror, and then as the rocket ship moves towards the right, they see the light also move to the right because it needs to hit that top mirror where the spaceship now is located. So they're actually seeing that light moving at an angle. And then as the light bounces back down towards the bottom mirror, they don't see it bounce straight back down. They see that light moving diagonally to um, get to back down to the bottom mirror and the new place where the spaceship has now moved to. And so for the person there on the left, they're seeing that light move fairly quickly. And obviously it's moving way too quick for you to see, but if we could slow down those measurements and see the light moving, they're seeing that light move straight up and straight down. So it's a short distance over a short time, giving them always the same value of c. In the picture on the right, they're seeing the light move over a longer distance because the rocket is moving or the spaceship is moving, and they're seeing, and it's taking a longer time. So the same event is taking less time for the person on the left and more time for the person on the right. So when we talk about time dilation, um, the same event can take different amounts of time depending on where you are observing the light from. Due to this fact, though, clocks actually tick more slowly when you're moving than when you're at rest. Clocks will tick slower and slower as the spaceship approaches the speed of light. When we see a rocket traveling at close to the maximum rate through space, it if we could see it moving up to the speed of light, then time would basically stand still if you could actually move close to the same speed of light. So the closer you get to the speed of light, the slower time goes. Time dilation does not have anything to do with the mechanics of clocks, but due to the nature of time itself. Again, as we saw in that last picture, that to the person standing on the ground watching the spaceship go by and the light moving, it took more time for that light to move up and down than it did for the person on the left who was inside of the spaceship. So the clock, there's nothing different about the clock as it moves at different speeds. It's just ticking to the rhythm of a different time. Time dilation has also been confirmed for not so fast motion. In 1971, they wanted to test Einstein's theory, so they sent 4 cesium beam atomic clocks flown around the world twice on jet flights, and 1 clock was flown eastward and 1 clock was flown westward. At the end of this, the clocks indicated different times after their round trips, and the observed time differences, which were only in billionths of a second, but they were in accord with Einstein's predictions. If identical twins were to one stay on Earth and one take a trip into space, then when the twin who goes out into space returns, he's going to be younger than the stay-at-home twin. And how much younger he will be depends on the relative speeds involved. So if the twin that goes into space is traveling at 50% of the speed of light for 1 year, the space twin will age 1 year, while the Earth twin ages 1.15 years. If the space twin was traveling at 99.5% the speed of light, the space twin would age 1 year and the Earth twin would age 10 years in that time. So the faster that you go, the closer that you get toward the speed of light, the more significant this time difference is between the person staying on Earth and the person traveling through space at a faster speed. And again, if you're traveling at a faster speed, time is going to go slower and you will not age as quickly as someone going a slower speed. One of the old arguments against space travel was actually that it would take too long. And this seems very logical that if, let's say, the nearest star after the sun is 4 light years away and a round trip to even the closest star at the speed of light they would have said would take 8 years. Now, can you think of a reason why this might not be a valid argument? And a hint is it has to do with time dilation. So with time dilation, an astronaut traveling at 99% the speed of light could go to the star Procyon, which is 10.4 light years away, and back to Earth in only 3 years astronaut time. Now, on Earth, because it's 10.4 light years away and 10.4 light years to return, about 21 years would have passed on Earth. But for the astronaut, they could have done all that in only 3 years. And that's again if they could go 99% the speed of light, which at this current time, we're not going anywhere near that fast. Now, the other component to length contraction or to time dilation is length contraction. And as an object moves through space, space as well as time changes. In a nutshell, space gets contracted, making objects look shorter when they move by us at quicker speeds. So let's look at this baseball not moving at all. It looks nice and round. The closer you get toward the speed of light, the space of that baseball actually becomes narrower and narrower and narrower, so it actually takes up less space. And if you could actually approach the speed of light, then that baseball would take up no space at all. So what does length contraction mean for space travelers? It means that as we speed up, space contracts, meaning that as we approach the speed of light, it takes less distance to get somewhere. At the speed of light, we could travel 25,000 light years instantly because the distance would be contracted to no distance at all, just like the baseball in the picture above. Now, we can't actually travel the speed of light, and we don't actually have the technology to get anywhere near that, but the faster that we have the ability to go, the less space we would have to travel to go that distance. Next, we get to move on to Einstein's famous equation, E equals mc E equals mc squared. So what Einstein found is that a piece of matter, even at rest and not interacting with anything else, has an energy of being, or what they call rest energy. Einstein concluded that it takes energy to make mass, and that energy is released if mass disappears. Um, the amount of energy is related to the amount of mass by his famous equation, E equals mc squared. What that means is that energy is equal to mass times c, again the speed of light, squared. E equals mc squared in regards to nuclear power. And this is a good example. So nuclear fission, or breaking apart an atomic nucleus, gives off incredible amounts of energy, and it also gives off a tiny amount of mass. Now, if you think about it, E equals mc squared means that the energy is equal to your mass given off times the value of c squared. And remember, c itself is 300,000 kilometers per second. So c squared is going to be 300,000 squared. It's a huge number. And when you multiply that huge number by even a tiny, tiny change in mass, you're going to get a huge amount of energy given off. So because of this, nuclear fuel will weigh about a gram less for every kilogram of fuel that undergoes fission. And the formula doesn't just apply to things like nuclear or chemical changes. A cup of tea would actually weigh more when it's hot than when it's cold. And because a warm cup of tea contains more energy and therefore it will weigh more. Now, you can't actually do this experiment at home and go weigh your cup of hot tea and cold tea because the difference is so minute that you won't be able to measure the change in mass. But if you could measure very, very minute differences, you would see a different mass or different weight of that cup of tea when it's hot versus when it's cold. Essentially, what this formula means is that mass and energy is the same thing. Mass is just concealed energy. And if you wanted to know how much energy is in a system, you could just measure its mass. For an object at rest, that energy would be the mass, called the rest mass energy. And with motion, the energy is even greater. So it has that rest mass energy plus its energy due to motion. That's the end of our week 9 lecture, and that's the end of our lectures for Physics 103. Thank you all very much for all the hard work this term, for all the feedback that you've given, and I hope that you have a great end of the quarter for all your classes. And if you have any questions as you prepare for the final, please let me know, and I'll be happy to help you get ready for that. So the final will be due on Wednesday of finals week, so please make sure that you make some time to get your final completed and give yourself time for those multiple choice questions and essay questions. Again, due Wednesday of finals week. I think that's it. So if you have any other questions as you go about your week 9 and week 10, please feel free to let me know.